Okay, so we've all asked ourselves this question at some point in our lives, like, what is E? And it's a good question, but I think the thing is to not get too bogged down by it, but rather to just like see where it comes from and then understand like what that tells you about the situation here. Okay. So like the main thing to know about the function e to the x is that it's equal to its own derivative. Okay? So, I mean, we can cheat a little bit and take a look at like what e to the x is doing. It does something like this, whatever. Sorry, it's a bit abrupt, but the point, anyway, well, we know that like anything to the 0 is equal to 1. Okay, so we would hope that this is 1, and anything to the 1 is equal to itself. So we would have to hope that this is E. But the question remains, like, what is this number? Okay. Well, let's just consider f of 0. Well, we're going to consider the behavior of these two functions at x equals 0. Okay. So we want to look at the behavior of f, and we want to look at what we know based on this relationship. This tells us about the derivative of f. Okay. Well, we know that the function value of f at 0 is 1. Okay, and we know that it equals its derivative, so we would have to have a 1 in the derivative. But wait, there's a problem there, because if you differentiate this function, you get 0, which means that there has to be some other term here that differentiates to get 1. Okay, well, how about x squared over 2? Well, that would do it, because the derivative of this is just sorry, I lied. X would do it, because x's derivative is just 1. Okay, so we're done. No, we're not done, because anything that's in f has to be in f prime. So we'd get an x here. Okay, so we would need to find something now whose derivative is x. And this is where we get our, sorry for the spoiler, we get x squared over 2. But then we'd have to add that into the derivative. And we'll do one more term here. What is the antiderivative of x squared over 2? Well, it's got to be something to do with x to the 3rd. And we need to cancel out the 3 but keep a 2. So if we did 3 times 2 is 6, that would do it, correct? So anyway, basically there's a pattern here. And the pattern is that f is equal to 1 plus x squared over 2 factorial plus x squared over 3 factorial plus forever. And so, in a lot of the time, you'll see, well, e is the base of the natural logarithm, and it's equal to 2.71828, blah, 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 blah. Well, where that comes from is if we evaluate f of 1, meaning if we let x equal 1, get 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 4 factorial. What's that? 4 times 3 times 2. 4 times 3 is 12 times 2. 1 over 24. This is equal to 2.71828, blah, 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 blah. Okay. So that's one way that you want to think about E. And there's another good way to think about it, which is to think about compound interest. So basically the spoiler here is, okay, if you have $1 and 100% growth, that is to say, doubling in 1 unit time. And I'm putting these in quotes because, like, the hard thing to get your head around here is this is what you would get if there was only one calculation of your interest at the end of the time period you're dealing with. But we have, if you have $1, 100% growth or doubling in 1 unit of time, under continuous compounding. And the dollar amount after 1 time unit is equal to the limit as n goes to infinity of 1 plus 1 over n to the n, which is equal to, drum roll please, E. So, I mean, the thing that we want to point out here is that, like, you could have started with some amount of money other than $1, okay? And you could have had something other than 100% growth or doubling. Okay, and basically, like, if you started changing those things, I'm not going to derive it right here. You can watch Khan Academy if you want to see that. But basically, if you take the amount of money you have is going to be equal to, like, what's called, like, the principal, or the amount that you start with, times e to the RT. E is just sort of like the base case to the rate times time. So I think, like, what's important to see here is that, like, any time you're dealing with something that shrinks or grows in proportion to itself. Now you can obscure E by multiplying it by something else, and you can, you can do different things with the rate. You can, like, make what's going to happen faster. You're basically, like, when you change the rate, you're kind of like, you could think about it as you're reparameterizing. So instead of, like, only being allowed to go on along x, you could be going along x 3 times as fast. So, like, it was like 3t. By the time you get to here, you're already way up here. It's like this lets you, like, accelerate through time. Or I shouldn't, actually, that's bad word usage because we're talking about calculus, so it's like, I shouldn't say for accelerating through time, but it allows you to, like, progress through time at a faster rate. Anyhow, I think that's all I wanted to say. Oh, So my point is just that, like, anytime you have this kind of like growth or shrinking as a function of itself, like whether you're aware of it or not, and whether you know where it comes from or not, E is lurking in there, and these are two different ways that you can sort of get at like what that quantity is in particular. Okay, next we want to do log. Call this what is this? Technically, this is for categorical data analysis. Okay. Okay. So we just talked about what E is. Now we need to talk about like what log is. So, you know, we had this function here. Boop. This is f of x is equal to e to the x. Okay. So basically all log is then, well, you might think it's like a natural question to ask, like, you know, what is the inverse? And by this we mean, like, look, in this function we're going to put in an x value and we're going to get out a value of e to the x. Now we want to find, we'll call it g. We want to find a function that's going to eat I don't like how I'm going about this. I'm going to try something different. You know, I think maybe the thing to do, if we solve this for x, what does that accomplish? Well, let's say f was something simpler. Let's say that f was equal to x squared. Okay, then we could say that x is equal to plus or minus the square root of f. Okay, and we know visually like what's going on here. This is like x squared. Okay, and you know that plus or minus square root of x is something like this. So I mean, one thing to see right off the bat, and this will be true for any functional inverses, is that like there's symmetry about this line y equals x. And what's more is just to see the basic relationship that like these two functions sort of undo each other. Meaning if we take f of 2 is equal to 4. Okay, if we take this function value and we run it through the inverse function, I think we've picked up a plus or minus here, but the main idea And we've picked that up because well, how have we picked this up? I mean, the main thing I wanted to show is that, like, this function, if you do f of some x, you get a value, and if you do f inverse of that value, you get back like what you started with. I mean, that's the main point. So these functions, in a way, can be said to like undo each other. So the question is there such a function for f of x, for f of x equals e to the x? So the question is, we want to find something, we want g of x such that g of e to the x should just be equal to x. Okay, well, that function is called log. Okay. So if we take the, and like, you know, you could say, well, where did you come up with that? Well, just let it exist. Let it be what it is. We want log of e to the x to just be x. So what's the motivation? Why am I allowed to do this? Well, we know that e to the x is just like, I don't know if I can explain it, but in any case, you're allowed to log it and swing it. And we know that the log of e is just 1. So this function does it. And so, like, what could this function look like? Well, we know it's got to be like the mirror image of this guy, which means instead of going off to negative infinity here, it's got to go off to negative infinity in y. Okay, it should hit the x-axis in the same place that this function hits the y-axis, which we said is 1. Oops, that's a big mistake. Really didn't like that. And it's got to do something like this. And this thing is going to grow without bound. It's not going to level out. It's going to, like, for any y value you give me, there will exist an x such that, like, log of this x is equal to that y value no matter how big it is. There will be an x that's big enough to do it. Okay. I think that's, so I mean, as you can see just from watching my trying to explain what log is, it's like it's not really clear. Like, I can't say that I know everything about it, but what I can say is, like, 1, it's a function so, like, I mean, I can justify a little bit why I was able to say this. Because I've claimed that, like, log undoes whatever e to the x does. So we know that f of 1 is equal to e, right? So that should mean that like log of e should be equal to our original function input, which is 1. So that's why you're allowed to cancel this out based on the rationale that I've defined this function to be like the inverse. Okay, so we know it's a function that's defined, well, it never hits 0, so it's defined on x has to be strictly greater than 0. But other than that, it can go on to infinity. And we know this. We know the range of f is negative infinity to infinity. And thirdly, we know is the functional inverse of e to the x. Okay, so we're going to leave that there. Let's look at our first guy just to remember what's next. Okay, so then we need to do what is odds, what's a linear probability model. Okay. So I guess the thing here is just to see the difference or the connection then between odds and probability. So suppose you had like 3-to-1 odds to win. What does that mean? That means you'd expect 3 wins out of every 4 tries. So basically your probability, in a situation where you have 3-to-1 odds, your probability of getting the thing is 3/4. So it's very important to see the general relationship. Odds over 1 plus odds is equal to probs. Okay, and this is going to be very, very important. And just to show that the sword cuts both ways, like let's say you had a 1/5 chance of success. Probability of success is equal to 1/5. Okay, so how would you turn that into odds? Well, we use this equation. Odds over 1 plus odds is equal to 1/5. 1/5 plus odds over 5 is equal to odds one-fifth should be equal to odds minus odds over 5, 5 over 5. So then we would get 4 times the odds over 5 is equal to 1 over 5. ones can cancel, and we get odds then are going to be equal to 1/4, which implies that you've got sort of like a 1/4 to 1 odds of losing, or if you will, 4-to-1 odds. Sorry, that was a winning of losing. Oops, spelling problems here. Okay, so if you have 4-to-1 odds of losing, the probability of losing is equal to 4/4 plus 1 is 5, which means that your probability of winning 1 minus 4/5, which is equal to 1/5, which is what I started with. Okay, so the point is just to see that you can interchange between the two. And this becomes very important in logistic regression because your entire interpretation of the model hinges on keeping this equality in mind at all times. Okay. So let's take a second and look at like a linear probability model. Okay. So suppose we have a binary outcome, like we're going to call this y, and what it's all about is like accepted to school, which will be equal to a 1, or rejected, which can be equal to a 0. So we want to have one predictor in our model, which is going to be equal to like a test score. And when we look at the students, the range of the test scores, I mean, this is kind of, I'm ballparking, but you know, it's something between, say, like a 30 up to maybe someone got a perfect score. And we're going to look at, let's say sorry, I'm going to cheat a little bit and see what I had. So what I wanted, okay. Okay, so I made up 30 students. So basically we're going to look at we can call it study, because this is kind of like a retrospective study on something that's already happened. But we're going to study what the outcomes of 30 students. Okay. So for each student, they're going to get, I'm going to call this the observation number, we could call this test score, and we could call this set. So our data will look something like this. 1, 2, 3, down to 30. Test score might be like 82, 71, 63, 98, blah, 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 down to like 62. Okay, great. accepted, yes, no, no, yes. Now, okay, so we're going to get something like this. Now, how could we, well, it's actually, like, it's pretty intuitive. Like, if we plot these points, you know, we might get something like this. This is 0, this is 1. So this, the y-axis here represents whether they were accepted, and the x-axis is the score. Okay, yeah, so there's might be someone here, there might be someone here, 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 here. Okay, so you might get something like this. So, like, a reasonable thing to do, I think, if you're familiar with these kind of, with this kind of situation, I mean, you could do like a linear regression, right? And you would get some kind of line like this that has some kind of intercept and some kind of slope. Rise, over, run. Anyway, this is the slope, right? And what you would be able to do is you would be able to input an x value, and this should tell you, you know, something about the probability that you get accepted. And this is called a linear probability model, just for this reason. So we could say the probability of getting in, which we can call pi, as a function of x, is just going to be a plus b x. Okay, so maybe we take a look at this in R. Okay. Oh, is this how you spell rigged? Because I didn't want to say rigid. I definitely wanted to say, is rigged with a W? Yeah. Good. Everything's okay. So we're going to rig this data frame where we're saying basically that test scores are systematically higher for those who are accepted to the program. So I'm going to make this data frame, and the way I'm going to quote-unquote rig it is, look, for my accepted, I've decided to do 10 people, and I'm actually going to switch this because I said I wanted accepted to be 1 and rejected to be 0. So I'm going to have 10 people that got, sorry, you can't see if I point to the screen directly. You got 10 people that got in, and you've got 20 people that didn't. And then what I'm saying is, for the test score data, I'm going to make that up too. And I'm going to use normal deviates from 80, 10 of those, and from, let's make this a little bit more dramatic. Let's say that the mean for the people who didn't get in is 65. And just to spice things up, we'll give them kind of like a larger variance. Oh, let's just do that. Okay. So let's create this data frame. Data frames are the bomb, by the way, in case you haven't gotten into using them. Something was very, very grumpy. And the grumpiness is because of that. Okay. So let's take a look at this data frame. Okay. So this looks plausible. Like, if you actually went out and did your survey of 30 people, like, this might be the kind of thing that you see. Okay. So what if we, okay, first of all, I need I'm going to do this, attach new data. Okay, so to explain why I just did that, now, okay, if you've worked with a data frame, you know you can just say, like, if you wanted to get a column from the data frame, you would put the name of the data frame, $, and then, like, the column, right? Well, if you just put attach, now you don't have to do that. Now you can just be like, you know, you basically let R know that, like, this is the thing that you're talking about. Okay, so we've got that. So let's just take a look at this thing. So we want on the x-axis, we want test score. And on the y-axis, we want accepted. Okay, so this looks pretty similar to, like, my completely made up little drawing here, right? Okay, fair enough. Now what I want to do is that linear regression that I talked about. And I want to do it. And I want to pop this line through it. Let's see if R is happy about this stuff today. Interesting. So I get something like this. Okay, so what have we done here? We've created a linear model. Okay, and basically it's going to have this kind of form. And I'm just going to say 0.03 and minus 1.7. Was that about it? Okay, so here's the cool thing now. Now that I have this, I can input any test score and get at least an estimate for what I think the probability is going to be of getting a certain getting accepted or not. So let's try that. And I mean, I don't think I have it coded there. Well, maybe I do. So sorry, this stuff is no longer relevant because I changed everything around. But basically, look, this is going to, it would be to our benefit to simply make a function, let's call it simple regression. It's going to be function of a single variable. And all we want to do is we want to take 0.03 times x, and to that we want to add minus 1.7. Actually, and what I should do is maybe I should call it, maybe I should be more descriptive and call it linear probability model. Okay. So I'm going to go put this into R and see whether R likes it or not. So let's say somebody got an 88 on the test. What is the probability of them getting into the program? 0.94, that looks good. What about a 77? Okay. Hey, this is great. I like this. But I have a feeling something bad is going to happen. The thing is, in our data, nobody did really poorly. A probability of -0.5. Well, that is not possible, but somebody could certainly possibly get a 40. What about a 99? Oops. Yes, 99 does equal 99. We know this. So if you got a 99, you would have a 127% chance of getting in. Okay, so we can see that basically what have we learned here? Although this is a nice idea, it is flawed beyond all hope. Okay, so basically we have to do something better than this linear probability model. And so, like, the answer to our problem is to see how you might use a logistic function So basically, a logistic function is going to have the form of this. And some of you might know that if you just multiply top and bottom by e to the x, this could also be seen as 1 over 1 plus e to the minus x. So these are equivalent. But actually this form is the guy that you want to see. Okay. So like, what does a function like this do? Well, we can take a look. Do I have one in here? Yeah, sure. That's kind of a spoiler. Here's what I'll just make a new one. Okay, so this is going to be, comment here is, see how our linear model fails. This is see what a logistic function looks like. Okay, so we're going to have logistic is going to be equal to a function, single variable, and all we want to do is get e to the x over 1 plus e to the x. Okay. And let's plot this. And let's do so from what? Negative 20 to 20. Okay. So basically what we end up getting here is what's called a sigmoid or S-shaped curve. And this S-shaped curve has a very desirable property that we want to take note of, which is that as it goes to negative infinity, it approaches 0, and as it approaches positive infinity, it goes to 1, but never gets there. So this logistic curve is really handy for modeling a probability, right? Because if we can get the like reasonable range of our input, sort of where this S is happening, then those are going to be very improbable, but still possible. And sort of the meat of the distribution is going to be like where we're seeing the action in this curve. Okay, so I think that's just about all I wanted to say there. Sorry, I don't feel like thinking. I just want to know what it is that I said I was going to do. Okay, logistic equation. Okay, so this is what we want to see. We want to see like what it is that a logistic regression is going to do for us. Okay, so first of all, we want to know like what, well, I guess it's the same as with the linear model. You have to give the computer data such that we have like a binary response outcome like we did with the test scores. With a binary response that's going to be we have a binary response, and the implication, or how would I phrase this? The assumption is that response is a linear function of the data. Okay, and so what this means sort of generally, I guess, is that if you've got your response, and it's going to be equal to your data matrix times like some vector of coefficients. So this is the idea. You're gonna give your computer this data, and you're gonna suggest, there is room for like interactions between variables here and whatnot, but we just want to simply see that like we're putting in data, and we're assuming that there's some kind of like handy linear relationship between the data and the outputs, and that relationship is modulated or controlled by this vector of parameters, which we're going to use the data to estimate. Okay, sorry, I don't want that dot there. Right, so like what is the computer going to do? Well, this much is not so clear to me. But what I do know is this. You're going to give the computer data, and it's going to spit out a linear model. Now, don't confuse. This is not the same as the linear probability model that we seen before. The computer is going to do something crazy, and it's going to give you I'm going to stop using alpha. I think alpha is stupid. I'm going to just start using beta now. Well, these are now estimates, but it's going to give you something like that. Well, in our case, there was only one input variable, so we're just going to keep it simple and say it's something like this. Why do I keep doing this? Well, it's going to give you these parameter estimates, and the implication is that you can put these into a linear equation. But there's more going on here. This logistic regression does not model like the output of response directly. Instead, what it's going to do is it's going to give you log of the odds of x. Okay. And so the idea now is you're going to get these parameter estimates. Okay. From that, you can feed in an x, and you're going to get some number, right? So like, let's just take as an example, let's say that like x equals 65. Okay. So you would get beta naught plus beta 1 times 65 is going to be some number. Let's just call it like y. And then what this thing is saying is that the log of the odds of 65 is equal to this y. And to like, just to sort of hint at how you interpret this, or how you would unpack this, you can undo log with this like anti-log deal. We know the inverse function of log is like e to the x, so you could say that like there's a reason why people say log inverse instead of actually writing e to the this. But in any case, you can take your inverse log, and then you would just get that like the odds of 65 are equal to whatever your y, would be equal to e to the y. And so you can like leave this as it is, or you can take it one step further and say that the probability of 65 is equal to, well, how do we move from odds to probability? We would say e to the y over 1 plus e to the y. Okay? So I'm going to show the example, and hopefully this will all make sense momentarily to both of us, to both my loyal viewers and myself. Okay. So where do I actually fit the model here? Okay, so this is it. Oh, and by the way, just like honestly disregard anything that I haven't mentioned explicitly. You should probably, oh well, actually this thing's kind of cool. I just show that when you take the log odds, you get back like the same line that goes into your exponent in this thing. But anyway, I'd seriously say disregard that. So we want to stay focused here. Okay, how does this look? Logistic regression fit is equal to GLM is the function call, because I'm doing a generalized linear model. I want a model accepted as a function of test score. Now the family here is going to be a binomial, because that's like what my outcome is. Now it is going to know to use to do the logit link function. Like it understands that that's what it's being asked to do, I think. In fact, a great thing to do would be to check that. Let us check this assumption. So let's say default link function family. Oh, come on, computer. I only have 800 things running at once. This should be fine. Family binomial. And the first thing that comes up is generalized linear model. So they know what I'm talking about. Right. So it's going to use this thing by default. So we don't actually have to specify anything else other than the family of the model. Okay? So I'm going to do it. Okay, so it's telling me that there was some kind of issue, but I'm not too worried about it. So let's pull the coefficients off of this thing. Okay. So we get something like negative 70.61 and the other piece of the puzzle was 0.921. Okay. So, I mean, our whole point in switching to this logistic regression model versus versus the linear probability model is that we didn't like that, when we put in 40 for a test score, they were telling us that the probability was negative 0.5. So what would happen if we put in a probability of, or a test score, let's say that x is equal to 40. Okay, so here's what we do. We'll go and plug in 40 times 0.9209 minus 70.607, and we get this thing. And we might be saying, oh dear, that thing's just as negative as the next. But what we have to understand is that negative 33.77 negative 33.77 is equal to the log odds. Okay. Well, what does this mean? This means that e to the negative 33.77 is going to be equal to the odds, which means that the probability of getting in should be equal to e to the negative 33.77 divided by 1 plus e to the negative 33.77, which is have x equal to e to the negative 33.771, and so then we would just say x over 1 plus x. Okay, and so what do we get? We get an insanely small number, but it's not 0. So we can conclude something stupid small like this. Maybe let's just see if this thing is actually happy within sort of like our good range. So what if our test score had been this person should be kind of like borderline, right? Okay. Okay. So according to this thing, if you got a 78, you have a 77% chance of getting in. Now, what did I say, 78? Now, like, go look at our data frame. Well, the mean score of someone that got in was 80. So if you got almost an 80, there's probably a pretty good chance that you're going to get in. What about my guys who got like a 65? That's the mean score of the people who didn't get in. Maybe I call this a 63, so slightly below average for these guys. So now they're saying that this guy has a nearly 0 chance. But I mean, that's actually safe to say, because if you were below the mean score of someone who didn't get in, there's no way you're going to have gotten in. What about something that's like sort of happy in between? What about a score of, sorry if this is really tedious, but okay, their mean score was an 80 and theirs was a 65. So what if you got like a 70? What if you got like a 73 or a 72? What would you, do you think you would get in or not? I think it's a tough call, and this is why. So there's very little chance. 3% chance of getting in with that test score based on our data. Okay, well this has been very fun. I feel like there's something important that okay, so there's one more thing that really needs to be dealt with. So we've showed how to like do the logistic regression and how to like use the intercepts that the model gives us in order to like make some probability statements. The question is how to interpret the parameter value itself. Because what did we say? We said that like beta 1 was equal to, I have it written down right here. It was 0.921. So here's the question. Sorry, I'm just going to delete this because I don't feel like opening a new slide. Okay, I guess the question that remains to be answered is like, okay, in this model, how do you interpret a 1-unit change in x? Okay. Well, look. What I would say is we know that with x you're increasing your probabilities, right? So the question is by how much? So how much are the so I guess you could ask a few different questions. You could ask like how much are the odds changing? But you could also ask how is the probability changing as you go from x equals x1 to x equals x1 plus 1. Here's the question. Okay, so this shouldn't be so hard to see. Look. My claim is that the probability of x times some number, and this is where I'm cheating because I know it's times, I know it's not plus. But the probability of x times some constant c. Where's my plum? There it is. Should be equal to the probability of x plus 1. Okay. Now, what do I know about the probability of x? Well, I know it's equal to e to the, we know what y, like it's okay for me to write this, right? We know that that's referring to my a plus bx. Oh, I can't write that. Sorry, I need to go back in time here. Okay, I'm going to continue this over here. Okay, so what we're saying, and actually what I want to do is I want to use that alternative form of the probability. So I want to say that this is 1 over 1 plus e to the a plus bx times some constant c should be, sorry, this is minus, should be equal to 1 over 1 plus e to the minus a plus b x plus 1. Okay? Everyone so far so good here? And so the question is, I just want to solve this equation for c. How hard could that be, right? Okay. Well, okay. For one thing, okay. If these two fractions are equal, like look, if like 4/5 is equal to like 8, to like c over 8. If that's true, I mean, it's certainly the case that 5/4 would be equal to 8 over c, right? Well, I mean, in this case, c would have to be like 32 over 5. Okay, so just to like verify, I can just take any fractions and like flip. I can flip everything on both sides of the equality, right? And still have a true statement. 8 over 32/5. Okay, and 5/4. Okay, so I like that. I believe that I can do this. So here's what I'm going to say. I'd rather work with this. I'd rather say one plus e to the negative a plus b x over c is equal to 1 plus e to the negative a plus bx plus 1. Okay. Now, I mean, I know it's sort of inevitable. I have to like deal with some of this. So let's just say that this is equal to 1 plus e to the minus a minus beta x minus beta. Okay. So what do I say here? We can say this is 1 plus e to the negative a minus bx over c. Okay, you know what? I'm feeling pretty good about this. This is getting there. Okay. So what happens when we Okay, just as a little side note here, like 2 to the third times 2 to the fourth is equal to 2 to the seventh, right? Or let's say to the 3 plus 4. So like, what we could do is we could pull out an e to the negative b here, right? Okay. And now, if I replace 1 with e to the negative b over e to the negative b, what could I do? Well, I could factor out e to the negative b and say it's 1 over e to the negative b plus e to the negative a minus bx. Shit, I don't know how to reconcile this. You know what, the only thing I can think to do is to sort of start again and try again. Talk it through, figure this thing out. Okay. So we know 1 over 1 plus e to the negative a minus bx. Maybe my problem was the cheat. We want this probability maybe it's this probability but the thing isn't linear in probability. Maybe we should just look at the odds. We know that the log of the odds is equal to a plus bx. which is equal to the log of e to the a plus bx over 1 plus e to the a plus bx. So what I would say is that, like, so how about this? Log odds is equal to a plus bx. This means that this means that odds are equal to e to the a plus bx. This means that if we take the odds of x over here, and we take the odds of x plus 1 here, this would be e a plus bx. This would be e to the a plus bx plus b, which is the same as e to the b. So this means that c is equal to e to the b.